Yeah, just wait for them for a while. I don't know whether are they even armed? That's the thing. Yeah, sure, no problem. You just use the other one to join, so it's okay. Yeah, just give them some time to come in, or maybe I'll just start soon. Morning, Sonia. It's okay lah. It's okay. It's just like this is my morning face, so it's fine. Okay, when you guys are ready, let me know. Foolscap paper, I guess. For Sarah and Sonia, you don't have the paper, right? Yeah. So I think just try to recall the um the questions that you have done, you got wrong, and then you can kind of like ask me. The teacher hasn't gone through yet, right? Huh? The teacher went through already? Oh, that's terrible. No, that's not great. And then what? You haven't had it for so long. Okay. So I think you just try to take whatever you can take first. Take down the notes whatever works for you first, and then later on when you get your paper back, you just kind of like trans transfer the notes over. Okay. I'm going to start. Hang on. Yes, hang on. Your iPad doesn't have your login, I guess. Wait. 406646. 406646. No worries. Yeah. Yeah, no worries. Yeah. Okay. Once you're ready, I'll start, yeah. Okay. So for me, right, uh, I know it sounds a bit cliche, but honestly speaking, I'm not too worried about the grades itself, right? I'm more concerned about your understanding. So there's only the three of you, right? So at some point, at any point, if I explain something and you don't quite understand, right, please just like unmute yourself and pause and ask me, like, oh, like I need help understanding this. Okay, hang on. Sorry, the technical problems. Yeah. Okay. Wait. Okay. Um, does anybody need me to go through this one? No? No? Sonia? Okay. So, Sonia? No need, ah? Okay. So this one you all got it. This one? Okay, this one looks a bit more complicated. Okay, can. I'll go through this one. So what I'll do is, hang on, I just open a blank piece of drawing board first. Bit slow, yeah. It's usually not so slow. Okay. Yeah, no. What I'll do is I'll just take a screenshot of this question and I just paste it over so that I have more real estate to draw stuff. Okay, so the question is train moves along a straight track, accelerates uniformly between two stations, distance between the two stations is 300. So I think I think it's one thing, guys. I think it's one thing to write all the formulas. I think it's another, and I know that some of you will be like, wow, that's a waste of time. But I will just point out that it is quite important to visualize the thing, right? So those are the two train stations, and you got to learn how to underline the important points. So it's a accelerates uniformly. That's quite important. The distance is 300 meters. 300 meters. Okay. They tell you that the train's initial speed is 12, and then they say reach the second station at 24, and then they say the average speed. So the next clue, honestly speaking, the very big clue will be average speed. Okay, between the two stations, 18 meters per second. So that's a very big clue because if you, I think maybe for Nicolette and Sarah, you probably didn't attend this lesson with me. But I don't know whether I covered it during the very quick revision I done before. Average speed is total distance over total time, right? Total distance over total time. Okay, for Sarah and for Sonia, if you're trying to make some notes and all that, please make sure you write down the question number, which is question two, and then you write down all these. You can write down the working. You don't have to write down the question itself, right? Because that will be like a big waste of time. So write down all the workings, right? All the drawings and all that. Total distance over total time. So they said there's 18, but somehow we know the total distance, so 300, and therefore in a way we can find the total time, right? So that was a clue, right? That statement there, right? This statement here, average speed. This is the like a really big clue as to what you're supposed to do with it, right? So sometimes it's not very obvious to you yet, okay? So sometimes just make use of the clues. Oh, they gave me average speed. I know it's total distance over total time, and they give me a value for it, and I know what's the total distance, so I can use that to find time. Okay, right. So that will be a clue. So 300 divided by 18, I expect that to be a okay number to have. Sorry, whoops. Uh, Hang on. Sorry, I'm not good with the things at all. Oh wow, that's a bad number. 16.7. Wow, that's such a lousy number to have. Oh, okay. So 16.7 seconds. 16.67 seconds. Okay. Ugh. All right, then they ask you what's the acceleration of the train. Okay, and that's pretty much it actually. So I can see that you did corrections and you drew a graph there, right? And you drew a graph there. That's great. I mean, that's the other way of understanding how to do this. I'll come back to the graph in a while. I think you tried drawing a graph, but I'm not too sure whether you made a mistake in that graph over there. But no, yeah, that's fine. So graph drawing is a thing. But it comes with practice. So you hadn't attended the earlier lesson, so probably probably need little bit more practice. Um, but yeah, so the time taken to travel from there to there, right, is 16.67 seconds. So which means you can think of acceleration as v minus u over t, right? And therefore acceleration is 24 minus 12 over 16.67. Okay. And I believe it should be something lah. I don't know what it is. So yeah, 24 minus 12, then 12 divided by 16.666. Let's see what happens. 0.72, right? So the acceleration should be 0.72 meters per second squared. Okay, right? So there you go. Obviously, my method and the green color corrections method is different, right? So let's talk a bit about like what that is. So if you decide to use, right, the graph method, just remember that it's a VT graph. So you got to put the axis as V and T, right? Because I see that there's no axis there. And yeah, you got to learn that if let's say your initial speed is 12, then you start at 12, then your final speed passing through, like, starting here and there is 24, then you go at 24, then the graph goes like this, right? Um, be very comfortable with sketching graphs because you will need this for physics, math, and chem, right? So, you gotta go very quickly. Okay, draw two axes, draw the two values, and then draw the line. How do we know that it's a straight line? Why is it not a curve? What if it's a curve like this or like that or like this? How do we know it's a straight line? Yeah, so accelerates uniformly means that the VT graph has constant acceleration, means the gradient is constant gradient there, right? So that's constant gradient. And yeah, all right. So the whole idea of drawing the graph is to understand that this thing here, okay, is 300 meters. Okay, yeah. So the area under there is 300 meters because that's the distance traveled. Okay, so if you're using the graph method, the objective is the same. You're just trying to find the time value. Okay, so you can use the area of a trapezium. I hope you remember what's the area of a trapezium, which is the sum of the parallel sides, right? This side here and that side there, right? The sum of these two parallel sides. So 12 plus 24, right? Then half, right? And then yeah. So the area of the triangle, the area of the rectangle will be, sorry, trapezium is what I'm talking about, will be uh area equals to half of u plus v times t, right? So it's a different way in a sense, right? It's not similar to this one, okay? But it gives you the thing. So 300 equals to half of 12 plus 24, right? Then times t. Then you can use that to find t. Then after you found t, that's not good enough because they want you to find acceleration. So you should recognize the acceleration is the gradient here, right? So you will have to find the rise divided by the run, right? For this gradient here like this. Okay. Yeah, so kind of like two methods. Um, but I'll show you in a while why they work, okay? Right? I'll show you in a while why they work, right? Okay. Are you guys taken down already? Just give me a thumbs up once you're done taking down the notes. Yeah, the tick sign is fine as well. Yeah, yeah, cool. All right. So one of the key things, and I think a lot of teachers actually don't say this, is that if you have uniform acceleration, hang on, let me just erase all of this. So I'm going to erase all of this now, except for the question itself. If you have uniform acceleration, okay, and you have initial speed 12, final speed 24, then one of the ways is to learn that average speed, right, is equals to half of u plus v. Yeah. So kind of like you take the initial speed, final speed, and then you halve it. That's actually the average speed, which makes sense because this is like half times 12 plus 24, right? And then average speed is 18, right? Which is true. Okay. But the problem is like knowing this piece of information sometimes doesn't really help you at all. Yeah, I mean, okay, great. Both sides are 18. Then what am I gonna do with that? So sometimes, it's just a useful thing to know, right? Average speed is the initial and final speed, right? And then half of it. But more importantly, is really the graph method as well as the formula method. That's the way it's gonna get the marks. Okay, let's go on to the next one. Question three: two objects, same size, same shape. One is heavier, right? Both objects dropped in vacuum, air resistance negligible. Compare the motion of the okay, compare the motion. Okay, oh gosh. A bit regret because I realized that I I think I didn't go through this one, and there's this video as well. Hang on, let me just I don't know if Zoom can show you the video, but okay. So this is the falling in vacuum. Right. Okay, I'm using Zoom. I don't know whether YouTube will show up on Zoom. You guys can see this? Okay. Okay. I'll send you the link, but this is just to kind of like I wanted to show this in class. This is just to show you that okay, what this guy is doing, Dr. Brian Cox, he is trying to drop two objects in a vacuum chamber. And this is one of the biggest vacuum chamber on Earth, like built on Earth. Like literally it's one gigantic container and they're gonna suck the air out of it. Okay. So I'm not gonna show you the whole video because that's like 4 minutes long. It's gonna be like a bit long to watch the whole thing. Um, but firstly, this is him dropping um yeah. So this is him dropping the two objects in air. Obviously, there's the chamber is not vacuumed out yet because he's still standing there, right? Otherwise, he'll die, right? Okay, hang on. So this is what happens when you drop feathers and a bowling ball, right? Obviously, the feathers, yeah. Okay. So because air resistance, right? So what they tried to do later on was to suck out all the air. So obviously he can't be inside the chamber when they're sucking it out. Yeah, you need an entire team. So this is what happens when there's a vacuum, right? You can see the feathers do not experience any air resistance, right? So you see even both the feathers and the bowling ball fall at the same rate. I don't like the fact that they showed the slow motion. They didn't show the actual speed of it because they don't fall slower. This video is slow motion, right? But you can tell that both the feathers and the bowling ball fell at the same time. Yeah. So anyway, uh, sorry. I'll just pause this here. Okay, so back to that question. Sorry, back to the question. So the question is going to ask you about two objects same size and shape, right? One is heavier than the other. In fact, right, if you're going to drop from rest in a vacuum, none of the size, shape, or mass matters at all, right? All like you can even have different size. You could even have feather shapes. Okay. So what I'm going to do is I'm going to show you the explanation using a diagram. So if you can draw this diagram as well, right? So so the keyword is in a vacuum, right? The keyword is in a vacuum. So if you had even if you had like different size and different masses, right? And this whole region here is in a vacuum, right? This whole region here is a vacuum. So the question is, we are supposed to describe their motion. We're supposed to describe the motion. Okay, let's not worry about which option it is. Let's try to understand what's happening here. Okay, trying to understand the motion. So the motion, you can see that they fall at the same rate. Okay, so if it's a vacuum, so we can say that they have the same acceleration, right? They have the same acceleration and they travel down the same distance, right? The same height here like this. Okay, the same height. That's the reason why they hit the ground at the same time. Okay, but they have the same acceleration, so they don't have constant speed, but they have the same speed at every point. So these two objects, right? In a while later, they will have like a bit more speed. A while later, they will have a bit more speed. Then a while later, they have more speed, right? So, but the idea here is that while both of them have the same speed, their speed is not constant. The speed is increasing, right? Because they're accelerating. So this is how you describe the motion. But all three of you have done dynamics in school already, so I need to use forces to explain. So I'm going to explain in terms of forces now. So I backtrack a bit. Okay, I backtrack a bit. That cleared the clutter. Let's talk about forces. What do the objects experience in terms of forces? This guy's a small mass, this guy's a big mass, right? So this one here has a small weight, while this one here has a big weight, right? So you have to understand both have different gravitational forces. Both have different, right, G forces. Okay, both have different weights. Okay, so their weights are different, right? Weight is gravitational force. The mass is different. The weight is also different, right? Mg is weight. Okay, mg is weight. This is the weight. It is gravitational force, right? Gravitational force, gravitational force. Okay, so now the problem is the thing is, are there any other forces acting on each of them? And the answer is no, right? So there's only this force, weight for this small mass, and the big weight for the big mass. Okay, that's their only forces. So those are their respective resultant force. So F net, right, equals to mg, and the F net for this guy is equals to big mg. So these are their respective resultant forces. Okay, so ma equals to mg, big ma equals to big mg, right? What I'm trying to show you that is that, oh, at the end of the day, both of them have the same gravitational acceleration. Okay, so that's why both of them have the same acceleration. And if you have the same acceleration and you're trying to fall down the same height, you will hit the ground at the same time. All right, at the same time with the same speed, but the speed is not constant. The speed is increasing all the way, right? So it's increasing, increasing, increasing speed. Just to be very explicit about this, like, for us, we use G as 10 meters per second squared, right? 10 meters per second squared. So again, what does 10 meters per second squared mean, right? It means 10 meters per second every second, right? That's what I said. So every second that we see that the two objects falling down, right, it will gain a speed of 10 meters per second. Please do not get confused thinking that, oh, this means that it travels 10 meters per second every second. That is wrong, right? Acceleration is not directly linked to distance. So however the height is, we still have to figure that out. I tell you what, how about I give you some sample values. Let's say based on that video, right, it took 2.5 seconds to reach the ground. Okay, let's say it reached, we already understood what is the, you know right, we already understood what is the idea of falling in vacuum. Falling in vacuum means both of them will hit the ground at the same time. So they hit the ground at the same time. Okay. So maybe my first question is, if they hit the ground at the same time, right, at 2.5 seconds, then what was the height? Right? What was the height? So very common mistake is some students will take, oh, you want me to find the height? Then I just take 2.5 seconds, I times this one, then it's 25 meters. Right? That's absolutely wrong. That's completely wrong. Okay. What you need to do is you need to find the final speed first. You need to find the final speed. We know the initial speed is 0. We need to find the final speed. Okay. So the final speed, oops, sorry, hang on. Okay. The final speed, right, is based on the acceleration. So since the acceleration is 10 meters per second, if I fall for 2.5 seconds, then the final speed is 25 meters per second. 25 meters per second. If you want to see that in an equation, there's just a equals to v minus u over t, and v equals to u plus at. Okay, that's just the final speed, 25. But that still doesn't help me find the height. So if you want to find the height, you will have to draw your vt graph again. All right, understand that it fell for a good 2.5 seconds, right? It fell for 2.5 seconds up here, right? This is 2.5 seconds up here. And then it fell for, and then the final speed it reached was 25, right? Then you can go ahead and find the area under the graph, and then this will give you the height, which by the way is, let me just work it out. 0.5 times 25 times 2.5, right? 31.25 meters. Okay, right? 31.25 meters. So that means that this height here is 31.25 meters. Right. So there you go. I mean, back to the question. After all that, back to the question. They ask you which is true about the heavier object. Okay. it cannot have a greater acceleration, right? It has a greater mass, that's true, but the same acceleration as a lighter object. So B is correct. It has a smaller acceleration due to a greater mass, that is wrong, right? It has a greater speed. So all these are wrong, right? Based on the video you just saw and my workings here, right? So this answer here is basically there's only one answer, right? B is the answer. It has a greater mass, but it has the same acceleration as the lighter object. Okay, and I proved to you using a video, and I proved to you using calculations as well, right? That they both will have the same, right, speed at the end. And they will, I mean, yeah, like, and we found out what's the final speed as well. Now, of course, the question will be, what happens if it's not a vacuum? What happens if it's air, right? So here's the thing. What happens if it's air? So let's say you have a small object and a big object, and then there's air inside. All right. For that sort of question, let's say this sort of question, the one with air inside, they're not gonna ask you to calculate anything. They can't, because air resistance is a changing value, right? As you fall faster and faster, you get more and more air resistance, right? At your level, they don't ask you to find like what's the final speed at the ground. They won't ask, they can't. That's impossible to do it. So because you have to understand, like as this thing is falling, right? As this thing is falling, it has its weight, and then there's the air resistance. How much air resistance is there? They would have to tell you. If they tell you, then maybe you can find some values here, but you won't be able to tell what is the value later on, because later on, as it falls further, the air resistance continues to increase, right? It continues to increase until it's equals to the weight, right? Likewise for the big object as well. In fact, the big object will fall faster. Okay, fall faster, right? But then the air resistance will be completely different from the small object. Okay. Yeah. And the big object, I mean, I drew it this way, but it looks a bit like deceiving. But yeah, the big object is gonna hit the ground first, right? Because the small object, like the feathers, right, will experience quite a bit of air resistance compared to its weight. So it will finish its acceleration earlier on, right? But the big object will continue to accelerate. In fact, since you all are here, I might as well just do this, because this will wrap up. This was something that I did in dynamics right at the end. So you know what? I'm just going to give you a VT graph, right? And this one has air, right? Has air resistance, right? Has air resistance. And I want you to draw both graphs. And the both graphs, one of them will look like this. The other one will look like this. Hang on, Then the question is, which one is which one? Obviously, this one is a small object, and this one is the big object. Okay, and again, it has air resistance. Right. Okay, I wouldn't say big, sorry. I would say, hang on. I would say lighter and heavier. Okay, lighter and heavier. So between the lighter and the heavier object, right? Let's say I give it the same amount of time. Let's say we look at I don't know, maybe 1.5 seconds, for example, right? I mean, look at this. Look at the area. The area under the big object, okay, it would have traveled more. In the same 1.5 seconds, the bigger object would have traveled more. The smaller object has traveled less, right? Which is that small area there, okay? So the heavier object is faster, right? But what you also notice is, for the small object, it reached its terminal velocity earlier, right? Lighter object reached its terminal velocity earlier. Okay, reach its terminal velocity earlier. So when you reach terminal velocity, it means that you don't accelerate anymore. And if you don't accelerate anymore, it means that your speed is not increasing anymore. So acceleration stops earlier, right? Reaches V terminal. I hope you guys are drawing all this down, because these are all your, like, right, reaches terminal velocity earlier, right? Has a smaller V terminal, right? So Yeah, there you go. So the lighter object, the reason why it takes longer to hit the ground, like the feathers, is because um, his acceleration stops earlier. He reaches terminal velocity earlier, its own terminal velocity earlier, and it has a smaller terminal velocity, right? So it will take longer for the feather to hit the ground. Okay, but yeah, this is the whole works, right? So I'm just giving it to you here like this, right? Yeah, I know that at some point, right, the questions don't matter really, right? It's all the extra things because today they ask you this, right? Later this year they're gonna ask you something else. They're gonna ask you, maybe they ask you to draw this graph. So I'm trying to go through all the aspects of that one question, right? I call it a deep dive if you want. I call it a side quest. Okay. But yeah, there you go. So B, right? B is the answer for this one. Okay, sorry. I'm gonna go on to the next one. How about your copy finish ready? Just signal to me. Nicolette, done? I know you got the question correct, but it's about all the other stuff, right? These are all the extra stuff. These are all the things that, huh? What's the what? Oh, what did I write where? This one? A stops earlier. Yeah, the acceleration stops earlier. Sonia, you done copying? Okay. Nicolette, okay, huh? All right, good. So that's for question three. Question four. Did anybody get this wrong or right? Question four. Oh, Sarah, I just realized your tick is like permanently there. Question four. I think this one here, if you remember my lesson, is just A, right? I hope you all didn't get this wrong, huh? I'm just gonna move on to the next one. If you need me to explain, please stop me. Sarah, Sonia, no need. Sonia? Okay, next one, huh? Okay, state difference between vector and scalar. Oh wow, yeah, hey, come on. You memorized this wrongly, Nicolette. Okay, what a waste, right? You could have gotten it. Because scalar only has magnitude. Okay, let me ask you this, okay? Do you know how to do scalar addition and vector addition? Just a very straightforward question. Like, what is scalar addition? Let's look at this now. What's scalar addition? Scalar addition. Okay. Scalar addition, right, is just you just take the value and add it up. Like for example, right? For example, 5 joules plus 25 joules, like energy. 5 joules of energy plus 25 joules of energy, that just gives me 30 joules of energy. That's it. You just add it up like that. Or even later on, you have like volts. If let's say you had like 100 volts on one side, and then you add it to negative 20 volts, right? Volts is a scalar quantity. So 100 plus negative 20, that's just 80 volts. And then that's it. Like, yeah, that's scalar addition. But vector addition is the problem, right? Vector addition will be the problematic one. Okay. So let's say you had a vector like this, all right, 5. And let's say you had another vector like that, 8. And I ask you, so what's the addition of these two vectors? You would have to draw a vector diagram. You would have to take this vector here, right, and move it over to here like this, right, so that you can connect its arrowhead and the tail like that, right? You don't angle it. You just shift it, right? You just shift it over, and then when you add 5 to 8, then this is the addition of the 5 plus 8 vector, the 5 vector plus the 8 vector like this. Yeah, that would be like the addition of the vectors. So vector addition would be a bit more problematic, right? Okay. Vector quantity displacement, that is okay. Right. So we have a vector diagram here. Does anybody need me to go through how to draw the vector diagram? This one is correct. No, Sarah? No need also. You know how to do this, huh? Okay. All right then. This one here. Oh boy. Okay. This one here. All right. So this is the classic velocity time graph, and they ask you to deal with things. So obviously, I know, like, velocity time graphs are always a bit of a problem, but there's some things for you to just memorize. Okay, you memorize that the gradient of a velocity time graph gives you acceleration. You memorize the area under the velocity time graph gives you displacement. Displacement. Okay, I'm gonna just screenshot this and put it on the PowerPoint, and then I want you to take down your own notes as well. Okay, right. So, yeah, what are the kind of, like, at some point, right? If you've done enough practices already, you can even anticipate what they're gonna ask me. Like what are you gonna ask me? You can, like, if you've done enough already, right? You can even tell them this. What are you gonna ask me? You can throw anything at me. You can ask me, right? I will know how to do all of this, right? So your mindset is that because you would have done all different aspects of this question already, right? Okay, number one, they can ask you this. Oh, what is the acceleration there? What is the acceleration here? What's the acceleration here and here? Right? They could ask you the acceleration. And if they ask you find acceleration, okay, no problem. I just find the gradient. Okay, so that's like the first thing. Then they could ask you, what's the displacement? Like, what's the displacement up to this point? Right? Then you can say, oh, that's a displacement. It's positive displacement. Or they may ask you, like, what's the overall displacement? If they ask you overall displacement, then you have to take the red area minus away the blue area. So overall displacement, sorry, Nicolette, you have to articulate. I can't hear you. Sorry. No, why would it be zero? Sorry. How do you find displacement again? One more time. No, no. How do you find displacement from a velocity time graph? Area under the graph, right? No, that's displacement. Okay, you got to get your definitions absolutely right. Do not try to adjust it to what you think you feel it should be. All right. Area under a velocity time graph gives you displacement. Like, that's a rule. It's not something for us to interpret or, like, be subjective about. It's displacement. And it's not distance, it's displacement. Okay? So if you have positive area up there, that's positive displacement. If you have negative area down there, that's negative displacement. So if I ask you to find what's the overall displacement at the 60-second mark, that is the red area minus away the blue area. Right? I'll explain to you how it moves in a while, but if you strictly follow the rule, then it's displacement. Red area is positive displacement. Blue area is negative displacement. Okay? And then if you take this area, you minus the area, you will get the overall displacement. Now I can show you step by step on what's happening to the car, right? But what I was trying to do was to just kind of, like, make it straightforward, right? The gradient gives you acceleration, the area gives you displacement. Like, that's it, right? Okay. Now I'll show you the step-by-step action of how this car is traveling. All right. So we have a car here like this. Okay, for example. Okay. We start off here. This is the velocity time graph. This is not a displacement time graph, but the area can show us displacement. Okay. So as this car is traveling towards the right, How do I know it's traveling towards the right? Because it's getting positive velocity, right? The velocity is becoming positive. So as it's traveling towards the right, the distance that it travels is this area here, right? So every 1 second, right, it covers a little bit more, a little bit more, a little bit more, a little bit more, a little bit more like this, right? So it's increasing in its distance. So kind of like his distance that he travels will get more and more and more and more like this, right? Which is according to the triangles that I'm showing you here. So the reason why I'm drawing you all the dashes here like this is because I'm trying to draw for you the rectangles here, the little trapeziums here. Okay, right? If you cut it all up, right? If you cut it all up like this, right? Then the dashes represents like how how long, like how much longer it gets. Hang on, okay. So let me just try to. Okay, then, as he continues to travel at constant velocity, he is now at constant velocity. He's still traveling towards the right. This is constant velocity. He increased his speed, he increased his velocity, and then he is now traveling at constant velocity. He's traveling at constant speed. So he's still traveling towards the right. He's still traveling towards the right. So the car has not at any point in time gone back to its original position. Not yet. Oh, sorry. Hang on, let me just get myself some space here. Okay. So you see all the constant dashes there, those are all represented by this. Okay. These are all the constant dashes here. Like, the each dash is like this area, right? That's the distance traveled. Then at this part here, what's happening to the velocity? The velocity is decreasing, it's slowing down, but it's still going to the right because this is still positive velocity. Look at the values on the y-axis, it's still a positive value, right? But it's getting less and less. So he's slowing down, but he's still going towards the right side. So he's still going further away. So it's getting less and less and less and less and less until he stops at this mark, right? Whatever the mark is, it looks like it's like 52 seconds or 51 seconds, right? So when the graph hit this point, and because you're asking me about this point just now, right? Like, where's the car? The car is there. The car is all the way there. How far? Whatever this area is, that's how far he is away from his origin. You understand this now, Nicolette? Then what happens is the car will then U-turn, right? The car will U-turn because that's exactly what happens here, right? He stopped already, but he's now going to hit the reverse and he's going to go backwards now, right? So he's now going to go backwards, right? He's going to reverse backwards now. And as he reverses backwards, at some point, I don't know where, the graph stops. I don't know what happens to him after this. I just know that he's probably somewhere around here. You get what I'm saying? Yeah. So this area here is that negative displacement there, right? How much he gone back by. So you got to learn how to read the graph. Okay, you got to learn how to read the graph. But here's the thing, I do have in my notes, right, in the kinematics notes, a very long thing that I kind of like skipped like I just kind of skipped. So I just tell you, I mean, I see this and I kind of want to tell you where it is in my notes. Hang on. Let me just show it to you. Sorry, my windows are ultra big on my screen. Okay, so if you go back to my notes, like I had these sort of graphs, right? Which I totally didn't go through because I was just like, oh, these are the minor steps. So I would suggest that you read through this graph. This is a displacement time graph. Don't be mistaken. This is a displacement time graph, right? After you read through already, you can look at the velocity time graph. I've got like two versions of it, right? So yeah, okay. So you can see this is how I describe the vehicle like this. You know how we describe every section. Yeah, but it's a one-time capital thing. Once you understand, I guarantee you next year you don't have to revisit this anymore because you already understood already. I don't believe that you are any of you is the type that, oh, I go through this, you understand this, next year you're like, oh, I totally don't know how to do. I totally don't know what the area under the graph means. I don't believe that at all, right? In fact, kinematics is one of the last topics of your A math, which means that at some point you will revisit kinematics again, right? So, I mean, it will benefit you if you understand this now. And then when it comes back to A math and suddenly you have to do kinematics, right? It's there. Yeah, it's there for you to do again, right? But yeah, okay. That being said, that all said, I don't know what they want. So I'm just going to look at the questions now. Right, first question, calculate the acceleration as it approaches a small town. Where's a small town? Oh, so it travels a constant velocity through the town. So you have to calculate the first gradient, right? Which is this one here. Ah, that's not fair. What kind of weird, what kind of a weird graph is this? There's no small markings. Huh? Oh, 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 so during the exam they sent a, sorry, Sonia? Sonia, sorry? Huh. Oh, I see, I see. Hang on, let me just take a quick look at it. Oh, they've got minor grid lines. They got minor grid lines. So, hey, do me a favor, guys. Next time send me pictures, try to send me upright, okay? Okay, there you go. Oh, I see. Okay, yeah, yeah, yeah. I was like wondering how come they didn't give you the minor grid lines. But okay, yeah. So you have to calculate the gradient here, right? That will give you the acceleration, right? That will be the acceleration there. Yeah. So calculate the acceleration as it approaches small town. I think this one here, right? The teacher is just trying to be a little bit tricky because they just want you to see whether or not you realize that he reached the town at this point, right? So the point he reached the town, right? Then he has to travel at constant velocity through the town. So this is the start of the town, and he left the town at 43 seconds. Determine the speed in km per hour as it travels through the town. Damn. Okay. So what they're trying to do here for B part one is they want you to convert. So the speed is what? What's the speed? What's the speed here? So that's 7.5, right? That's 7.5. So the speed is 7.5 meters per second. Look at the units, right? Right. Look at the units here, 7.5 meters per second. So your job is to convert 7.5 meters per second into km per hour. Okay. So I mean, I can show you the shortcut conversion. Ah, yeah, just times 3.6 lah, can already. But you won't be learning much if I just say that to you. So I'll teach you how to look at units, okay? 7.5 meters per second literally means the car travels 7.5 meters every second. It's a constant speed. It's a constant speed. So there's no the speed doesn't increase, it doesn't change. So every second that it travels, right, it will cover 7.5 meters. 7.5 meters, 7.5 meters, 7.5 meters, 7.5 meters. Okay? The question here is asking you, so how many km per hour is that converted into? Then you think about this. Oh, if that's the case, then all I have to do is just find out. If I travel 7.5 meters every second, right? Every second I travel 7.5 meters, how much would I travel in 1 hour? So 1 hour has 3,600 seconds, right? 3,600 seconds. So it's like, whoa, you know? So does that mean that I have to take 7.5 times 3,700, 3,600? The answer is yes. 7.5 meters times 3,600 meters. Okay. I mean, you can go and work this out. What do you mean why? Are you confusing minutes and seconds? 1 hour has 60 minutes. Each minute has 60 seconds, so that's why I use the 3,600. 60 times 60 is 3,600. So literally every second you travel 7.5 meters for a total of 3,600. But the final unit is they want it in km. So at some point you have to divide it by 1,000. So you can just take this 7.5 meters times 3,600 divide by 1,000, which then effectively, like I was trying to tell you, that there is a shortcut. The shortcut is just take 7.5 times 3.6, right? You will get your km per hour. Okay, so 7.5 times 3.6, right? So it's 27 km per hour. Like that's just straight up the answer, 27 km per hour, right? So that's the, yeah, I mean that question there is a bit like, they're a bit like naughty here, because like, usually we don't need km per hour, but now you're asking us to calculate km per hour. Okay, then they ask you to calculate the distance traveled by the car through the town, right? So I think one of your mistakes here is you marked it out wrongly, right? Like you marked the value wrongly. It's supposed to be 7.5, right? Yeah. So the 7.5, if you multiply it by the total time traveled through, okay, that will give you the, yeah, that will give you the total distance within, right? So yeah, I have to use this graph because there's no markings on the other one. So it's like 14 seconds and 43 seconds, right? And the well, you know why we find the area under the graph, right? For the displacement, the distance, right? Distance and displacement will be exactly the same if you didn't change direction. So as you're traveling towards the right side, if you didn't change direction, the displacement, which is the area under the graph, is equals to the distance traveled by the car. All right. So I hope you remember that I just said it. Huh? So yeah. And it's basically the area under this graph, because you're just taking your speed, which is 7.5 meters per second, and you're going to multiply it by a number of seconds. How many seconds is that? 43 minus 14. I'm so bad at this. 43 minus 14. 29 seconds. So you just times 29 seconds, right? That will give you the total distance traveled through. Understand this now? Yeah? Yeah. So that's the way to do that one. And then the last one here, yeah. So that's, I mean, he give you ECF, so that's fine, right? Just be aware that, you got to read the graph carefully. Like it's like you realize that this reading this wrong value here kind of like almost broke two parts of the question. And they want you to describe the motion of the car, right, between 51 to 60 seconds. Why you go and write 7? They give you that dotted one, what? You 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 counted it. You need a new ruler, is it? Huh? Your ruler. Okay, graph work, you better ask your math teachers to help you with your graph work if your graph work is bad. Okay. But yeah, I mean, we'll do some graph work from time to time. Okay, now the big question actually is this one here. Describe the motion between 51 to 60, right? This one here, oh, you got the 2 marks anyway, so it's fine, right? But this question here is the thing, right? So 51 seconds to 60. Look at that. It's so strange. 51 seconds is where's 51? Is that 51? Is this 51? Oh, hang on. Huh? No, it's 51. It's 51. Yeah, hang on. I mean, I have to look at this grid. I have to look at this grid. So they are asking from 51 to 60. Yeah, 51. So right here. So 51 second, what's up with the car? What's the car doing or not doing? How do you describe the motion at the 51 second? Guys, No, okay. So actually at this point, right, 51 second is literally at rest. Because the graph cuts the x-axis, right? It's basically a value of zero. There's no speed here. Like the speed is zero. Do you get that, Sonia? Yeah. So like at rest is literally at rest here. Hang on. Oh, what's going on? Oh, right. So it's at rest here. Okay. And then it's going to accelerate in the negative direction, right? It's going to accelerate in a negative direction, right? It has constant acceleration in a negative direction. It will achieve a speed of, from the graph here, I don't know what's this one here. How much is that? Is that negative 18.5? Yeah, looks like it's negative 18.5. Yes, guys. Oh, sorry, negative 8.5, sorry. Negative 8.5. Yeah. Okay, so yeah. Right. So there's one skill, all right? There's one skill with regards to this question, this one here. They describe the motion, right? When they ask you to describe the motion. Okay, just write this down. They ask you to describe the motion, you talk about the direction, you talk about the displacement, you talk about the velocity, and then you talk about the acceleration. Like that's what they want you to do. So you say that the car is at rest at 51 seconds, it starts moving in a negative direction, it covers a displacement of how much? You have to find the area here, right? And I don't care what the mark scheme says. If they ask me to describe the motion in the last 51 to 60 seconds, I'll just give everything to them. Because, I'm just like, I don't know, you didn't specify what exactly you want. You just asked me to describe the motion. I'm not gonna have to give it to you everything. So I'll tell them how many, how much, like what's the displacement, what's the area under the graph here, which you can find easily, right? Half times 8.5 times 9, right? Because this is like 9 seconds, right? And that will be the displacement. Then I'll say that the velocity is increasing at a uniform rate. You can say the acceleration is constant. And I'll give it to them. So I'll tell them how much is the acceleration as well. So the acceleration is, right, and the acceleration. So the displacement is this, and the acceleration is 8.5 over 9 seconds, right? That's the acceleration, right? So calculate the displacement, calculate the acceleration, tell them how much is it, what's the acceleration, is the acceleration constant, the velocity is increasing in a negative direction, and then that's it, right? Give them the whole works. More details. I understand whenever your teacher says elaborate, then you all start to repeat the same points, right? So don't repeat the same points. Give them more details. So talk about displacement, acceleration, velocity, direction. Okay? Because that's what they mean by describing the motion. Right. Yeah. Okay. Oh, what's this? So it rises with increasing speed, continues rising at constant speed, and it remains at 40 meters, drifting with no change in height, descends with decreasing speed, and lands gently on the ground. Okay. All right. So basically, you're asked to draw this graph, right? Okay. So I think the key thing is here, this one, right? Increasing speed, increasing speed. So from 0 to 5 seconds, so from 0 to 5 seconds, okay, increasing speed. This is a displacement time graph, right? So speed is basically velocity the same in the same direction. So, you know, the gradient of a displacement time graph gives you speed or velocity. Okay, so you can just change this increasing speed to increasing gradient of an ST graph. Okay, increasing gradient of an ST graph. Then the graph should look like this. Hang on, oh, whoops. Okay. Well, this is a bit tricky because you're supposed to. Okay. So this thing here, the first one is what? Is that no wait? How many marks is it to sketch the graph? 3 marks? Because you drew all of that as well. I see. Like, the points were given. Oh, the points were given. Okay, okay. Oh, but it's 3 marks. Wow, that's tough, man. I see. I understand. Okay, hang on, Okay, so but do you understand now that when the speed is increasing, you have to draw for displacement time graph the gradient increasing. So you can see that the gradient here is increasing, right? Okay, now hang on. I want to this is actually a very high level question. This drawing a curve going on to a straight line, right? This thing is actually an A level thing. But I guess, like I said again, they're bringing down some stuff. Let me show you there's a correct way of drawing this and there's a wrong way of drawing this. Let me show you the two ways, okay? Yeah, yeah. So let me draw for you the I think I know what your teacher is saying. But it's very unfair because it's very unfair. Okay, this is the ST graph, is a displacement time graph, right? They want you to draw increasing speed and then constant speed, correct? Just to be very clear on this, we are going to draw increasing speed with constant speed. Okay, that means you're increasing the speed and then it becomes constant. So your graph, right? Your graph needs to look like this. Right? So increasing speed and then all the way to constant speed, right? Increasing to constant speed, huh? So you have to draw it like this. If you look at it, you draw it like that, and then you're supposed to follow the curve. You're supposed to follow the curve like this, right? Follow the end point of the curve and then become a straight line, right? So this is increasing speed going on to constant speed. Again, don't forget this is displacement, right? Like this. So this is the correct way of drawing. Let me show you what's the wrong way of drawing. Okay, the wrong way of drawing will be something that looks like this. Let me use red color. This will be wrong. Like you see how you see, oh, sorry. You see how the gradient of the last part of the curve kind of like got changed, like or maybe it kind of like deflected a bit, then it became a straight line. So this is not the right way of drawing like such a graph, right? Going from increasing speed to constant speed. So I don't know whether teachers will mark students down for drawing a little kink here like this, right? It's not very fair because my goodness, that will be. I mean, okay lah, but there's a lot of marks, right? That's been given to this. So I suppose maybe as a learning point, you guys should learn this. If you're increasing speed going on to constant speed, your displacement time graph, you draw the curve, the gradient should end off in a smooth transition like this, right? Not a little kink like that, right? This will show you that. In fact, this will show you that the speed at the very last part has changed, right? The speed has decreased, right? So it's like you became faster, the gradient increased. Then at the very end of becoming faster, right? There's a sudden change in the speed like this. Then it became a straight line like that. Then the speed became constant. So yeah, okay. So this one here is wrong. But I don't know whether your teachers got mark you down on this now. It's just a bit high level question. Okay. Explain how the displacement time graph shows that the balloon is decreasing its speed during its descent, right? So you got to remember what's the relationship between displacement time graph and speed. It's the gradient. So you see, right, for what, sorry? Yeah, you can't. You can't, but you can draw tangents, right? Yeah, you can draw tangents. So if you draw tangents to the curve, if you want, you also can describe, right? As I draw tangents to the curve, right, I notice that the gradient of the curve is getting less. You cannot calculate a single value, yes, but the gradient at every point is decreasing. That's what a curve is, right? So I think for the earlier part of my kinematics lessons, right, I was drawing gradients like that. I was just drawing the tangent to the curve like this. I think Sonia would remember me doing this. Yeah. So I mean that's the answer. This is just straight up like that. It's like for 1 mark that you basically just say that the gradient is decreasing, right? The gradient is getting less steep. The gradient is getting less steep. Okay, gradient is getting less steep, huh? Hey, where did Sarah go? Okay. Then the forces here, is it? I don't remember she went out. Okay, that's fine. Just ask her to drop me a message. Okay. So then this one here, you got did we establish the forces already? Effect of air resistance can be ignored. Are you so annoying? Okay, so this is not fair question, constant speed, right? Okay, you draw let's say this is hot air balloon. You have your upthrust, you have the weight, right? You have the weight. Technically speaking, right, the upthrust must balance the weight and the, right, it's rising, right? Rising, so you should draw the weight like this, and then you should draw the air resistance like that. Yeah. Okay, I mean, I'll show you that this is the correct, absolutely correct way of drawing it. Yeah, that's yeah. Okay. So I mean, Nicolette, I believe that one no choice, because the upthrust is actually drawn um from the object. So your arrow starts from space here like this, right? So this doesn't show you that this force is acting on the hot air balloon, you see. Anyway, constant speed, right? Constant speed, the F net is zero. F net is zero. So if there was air resistance, your equations will be this. U is equals to F, the air resistance, plus the mg. Okay? But because your teacher said no air resistance, so the version of where's Sarah? Why Sarah come back again? Eh? Okay. All right. I mean, I'm about to finish, so let me finish it up. Sorry, yeah, I know it's a bit long, but I wanted to go through as many concepts as I can. So for your answer for this hot air balloon, the U and mg are balanced with no air resistance. So that's why it has to be the same length. So U equals mg. Sorry? No, that's a good question. That's basically you asking why is Newton's first law Newton's first law. What's Newton's first law? At the start, yes. When the balloon was trying to accelerate, yes. Okay, hang on, So let's say your hot air balloon is on the ground at first, right? Let's say your hot air balloon's at the ground at first, right? The upthrust will have to be bigger than the weight. Okay, what would this give you? Sonia, what does this give you? No, I got one force here, I drew it a bit longer. I got one force here, I drew it a bit shorter. What does this give you? Oh dear. It gives you a resultant force. Yeah, U minus mg equals to F net. And then when you have resultant force, you get, what do you get? Acceleration. So this hot air balloon will start to accelerate. Okay. Going up means being at rest at first, and being able to move up means you have acceleration. So in order to have acceleration, you must have resultant force. In order to have resultant force, one of your forces must be bigger than the other. Do you all catch all that? To go up, you need acceleration. To accelerate, you must have resultant force. In order to have resultant force, one of your forces must be bigger than the other. So therefore, then you can get acceleration upwards like this. Okay. Now, as long as the U is longer than the mg, is bigger than mg, you will always accelerate. But the question did say at some point that the hot air balloon rises, but at a constant speed. So that's the trigger. The moment they say constant speed, even if it's rising, means there's no Fnet. That means Fnet is zero. And if Fnet is zero, then we have to immediately accept that the upthrust is now balancing the weight. But it's still rising because Newton's first law. Because Newton's first law says that if you have zero resultant force, you could be at rest or at constant velocity. Okay? But I understand the most common mistake that students make for this part of their physics is not spotting the constant speed trick. The moment you see constant speed, it should be triggered that you write F net is zero. Like that's the first thing, like, oh, constant speed, F net zero. Constant speed, F net zero. Then you write down the equation, the U is equals to mg, they balance, but it's still rising at constant speed. No acceleration. No acceleration. Acceleration is zero. Okay? So this is your school's questions version, but please understand that for, like, in reality there should be air resistance. The F net is still zero, so the upthrust is equals to the air resistance plus mg. I don't know why the teacher said effect of air resistance can be ignored. That would be a bit weird. You should include air resistance. Yeah. So that should be the case. But of course, I think drawing three forces might be a bit, um how would I put it? Might be a bit too much for students. Yeah. Okay. I don't know. At Sec 3, I don't know, but maybe. But definitely at Sec 4, right? I would want you to know how to do this by the time you hit Sec 4. So usually this is the case. By the time you're at the end of Sec 3, you should know how to do this. Okay. Hang on. So they ask at 8 seconds, using ideas about forces, the motion at 8 seconds. Okay. This is the question. 8 seconds. 8 seconds. At 8 seconds, you have constant speed, right? At 8 seconds, the speed is constant. 8 seconds, the speed is constant. So why is the speed constant? Resultant force is zero. Why is the resultant force zero? Because the upthrust balances the mg. Okay, right. So they ask you using ideas about forces. Okay, right. So you have to say the upthrust. Now the upthrust is due to buoyant force. Hot air rises. Okay, if in case they didn't explain this to you, a force from air that keeps the balloon from falling. That's not good, man. This not good. Oh my god, that's such a bad way of describing it. Sorry guys, I feel bad for you. They shouldn't have called you this. They shouldn't have said this. They should have just said a buoyant force. A buoyant force due to less dense hot air in the balloon. No wonder, Nicolette, no wonder you drew the U pointing from upwards. Is that the reason why, Nicolette? No, no, as in, like, because he's saying it's a force from the air that keeps the balloon from falling. That's why you thought to draw it like this. Yeah, it's super annoying. They should have just called it what it is. Like, that is the correct thing. Buoyant force due to less dense hot air, right? Inside the hot air balloon. It's the same as this, guys. You take a ball, right? Guys, you take a ball and you push it underwater. you let go of the ball rises to the top of the water, right? Why? Why does the ball rise upwards? Because it's less dense, right? The ball has less density. That's why it will try to float. That's why it needs to go up. It's the same thing here, right? The hot air balloon, the air inside is hot, so it's less dense than the air outside. Since it's less dense than the air outside, this hot air balloon will have a upwards buoyant force. Okay, I don't know why what I feel bad for you guys. Right, please make sure that you all write this down. Okay, this hot air balloon, the U is actually a buoyant force due to less dense hot air in the balloon. No wonder this confused the heck out of you all. That one statement here, a force from the air that keeps the balloon from falling. That's not good, dudes. That's not a good thing to say. I mean, if you want students to learn, you shouldn't say this first. You should say a buoyant force due to less dense hot air first. That's not good. Anyway, but what's done is done is fine. Right? We just learn what is the right thing to do, what's the not the right thing to do. Just double check you guys written everything ready? Sonia, Sarah, Nicolette? Okay, good. So that's the thing, right? So when we say explain using ideas about forces, you literally need to describe all the forces. So you need to describe weight, you need to describe the buoyant force, and you need to describe resultant force, right? You have to say the resultant force is zero. The U balances the okay, not equals, balances, okay? Balances the weight, right? Don't use the word equal because they're not the same direction. So they can't be truly equal, right? Okay, balances the weight. Um, so the resultant force is zero, resultant force zero by Newton's first law, right? You should also throw in, if you throw in by Newton's first law, right? That's why the speed is constant, right? Or the velocity is constant. You know, your teachers will be like, okay, at least I know you know your thing, right? So based on Newton's first law. Okay? Are we clear on this? Just make sure. What? Sorry, where? Oh, sorry. Yeah, I forgot to talk about I forgot they said about Newton's first law down there. Yeah. Oh, I see. Oh, that's fine. Don't worry about it. Oh, last one here though. Okay. Um, Sarah, Sonia, let me just go through this last one. Let me know. Um, hang on, do you need this? Sarah and Sonia? No need. Sonia? No need, Then acceleration is not constant in terms of air resistance acting on car. This is exactly what I'm saying just now. This was exactly what I was saying just now. So you gotta listen to this, All right, and I'll finish off with this one here. Air resistance is dependent on speed. Air resistance, right? I usually like to label it as small f air, is proportional to speed. Okay, which means the faster the car is, the greater the air resistance will become. Friction is constant. Okay, friction is constant. So as this car is going faster and faster, if you know that the car is accelerating, how do we know if it's accelerating? It says here, right? It's accelerating. So if it's accelerating, that means the speed is increasing. The speed is increasing, okay? Which also means that the air resistance will increase. And if the air resistance increases, then the resultant force will decrease. Right? So if the resultant force decreases, then the acceleration will be different in a while. Like almost immediately, the air resistance the acceleration will completely change. So F net will decrease, A will decrease as well. Okay, so that's the relationship here. So if you look at this one, right, why the acceleration is not constant, right? You have to say that because the speed will increase, air resistance will increase, right? Yeah. Okay. Um, yeah. So this statement here is wrong. This statement here is wrong. And basically, I'll just end off by drawing you drawing the arrows for you. So hang on. Was it 900? Friction is how much? The sum of forces. Oh, 900. So total is 900. Okay. So I'll end off by drawing you this picture here. Okay, guys. I'll write on this one here. Okay. This is 2,500. 2,500. The collective sum of resistive forces is 900. Right? Collective sum of this one is 900. So is it going to accelerate? Nicolette? Why? Correct. There's a resultant force, right? Okay. But what happens immediately after this? Immediately after this, the car becomes faster, and therefore the air resistance will increase. The friction will not increase, but the air resistance will. So this 900 will become like what? Give me a value. What does it become? 1,000, right? 1,000. Does it still accelerate? Does the air resistance increase still? 1,100. Correct. So what happens is at every stage, right? At every stage, the overall acceleration of the car will continue to decrease. The acceleration will decrease. And therefore, if I draw the velocity time graph of this car, right? Everyone, I want you all to understand the graph will look like this. Okay? Right? I hope you guys are copying this down, right? Otherwise, I'm done here already. Like this is the velocity time graph of this car. If you have no further questions, I'm done for the day. Everyone okay? Okay. Thank you guys. Bye bye. Bye bye bye.